This is a problem of conservation of energy for a mass attached to a spring. So recall that at any time, the total energy of a mass oscillating on a spring is equal to 1/2 Ka squared, which is the sum of the kinetic energy plus the potential energy for all times. So in this problem, we're given the mass, 0.2 kilograms. We're given the frequency is 2 hertz. And we're given the velocity and position for a particular time. And it doesn't matter what that time is. So let's start answering these questions. Part A, we want the period. Definition of period is 1 over the frequency. So it's simply 1 over 2 hertz, or 0.5 seconds. Now for the second part, to get the amplitude, we're going to have to use that conservation of energy. So having 1/2 Ka squared equal to 1/2 mv squared plus 1/2 kx squared, I'm going to solve for A. So let's just leave it as a squared for now. The halves cancel everywhere. I'll have m over k v squared plus x squared. So we're going to need the spring constant. And the spring constant, by definition, is m omega squared, or m 2 pi f all squared. So working out the spring constant for this particular spring, we have 0.2 kilograms times 2 pi 2 hertz all squared. And we get a spring constant of 31.6 newtons per meter. Okay, putting that into the equation for A squared and using the velocity and position that we're given at that particular instant in time, we have the mass over the spring constant times that velocity, negative 0.3 meters per second squared, plus the position, 5 centimeters or 0.05 meters all squared. So solving that for the amplitude, we get 5.5 centimeters. Okay, part C, we want the maximum speed, and the maximum speed is given by omega A. That comes from differentiating the position function and taking out the quantity in front of the sign. So we have these quantities now. Omega is 2 pi f and times A. So 2 pi times 2 hertz times, we can just leave it in centimeters and we'll get centimeters per second for this maximum speed. Turns out to be 70 centimeters per second. Okay, and part D, it wants the total energy, and total energy is equal to 1/2 Ka squared. So we have 1/2 of 31.6 newtons per meter times 0.055 meters squared. And that comes out to 0.049 joules. Now there's another way to get that maximum total energy, and that's when the kinetic energy is at its max, 1/2 mv max squared. So putting those values in, you would get exactly the same value for total energy. You'd have to put that into meters per second squared, and sure enough, it's the same quantity for total energy.